Hi folks. So in this section we're going to be looking at logistic growth, which is a more mature growth rate. And luckily for us, not every type of population grows in terms of exponential growth. So let's take a look at these two. So here what we're looking at is typical exponential growth. As population gets bigger and bigger, its growth rate gets bigger and bigger. What we see on the right side is what we call logistic growth. And the growth starts off very slow, accelerates, reaches a max, and then starts to taper off. And after a while, the growth rate basically approaches zero once again. And the population is approaching a particular value, usually denoted as C, which is called the carrying capacity. So here we have exponential growth, and this is the idea of logistic growth. So let's take a look at the two differential equations which describe these types of growth. So what we see in the first case is our familiar differential equation for exponential growth. The growth rate depends entirely upon what the population is. Now take a look here. This one takes a little bit of thinking. And what we're looking at here is a population growth that, as we get very small, is approaching zero, and that's reflected by this factor. And as the population approaches C, this factor here leads also to dp dt being zero. So there's two places where dp dt is going to approach zero: when the population is getting very small, and when the population is approaching C. And that's why both of these terms have to be present. Now previously we have solved this differential equation, and we saw that it was actually pretty easy to separate variables. This, however, is a much more challenging differential equation to solve, and it's going to require a new technique of integration that we'll look at in a second. So, let's talk about what it means to integrate by using partial fractions. And the interesting thing is that this technique is really all about algebra and really nothing to do with calculus. So, I think the easiest way to get an idea, as usual, is to look at a simple example. And suppose we're trying to integrate this expression. Now, it would be great if x minus 1 was a factor of the denominator, but it's not. And so what we're going to do here is we're going to analyze this fraction. X minus 1 over 2x squared minus x minus 6. And it factors like this: 2x plus 3 times x minus 2. Right? And the thing about this technique is we actually work backwards. And what we say, okay, this particular expression right here might have come as the result of adding two fractions together, one of which would have as its denominator 2x plus 3, and the other would have as its denominator x minus 2. And really this whole task is finding out what should the numerators be. So I'll call that A, and I'll call that B. And now we work forwards, and we simply take this and add them together, and we're going to get an expression that involves A and B, and we'll figure out what A and B are. And then when it comes to integrating these two expressions, that will be easy because they will be ln's. So I'll skip a couple of steps here because, as we've said many times, you're pretty bright. But if I were going to be able to get a common denominator, A would get multiplied by x minus 2, B would get multiplied by 2x plus 3, and that would be my top. And my top would have to equal x minus 1. Now, if I were to get my numerator of this expression, the numerator would be, and you should do the work to convince yourself that it's true, a plus 2b times x plus minus 2a plus 3b. And that would have to equal the numerator on the original one, which is x minus 1. So therefore, what that means is a plus 2b would have to equal the coefficient on x, which is 1, and minus 2a plus 3b is the constant term, and that's minus 1. And so you know how to solve a system of equations, a two-linear system of equations. And if we solve this, what we get is a is equal to 5/7 and b is equal to 1/7. Okay? And so what we're going to do is simply take those two values for a and b and put them in here and integrate that. So stay with me. So making these substitutions for a and b, we see that we can rewrite our original integral as two separate integrals, and each of them is pretty easy to integrate. And so our integral is equal to 5/7 times the ln of 2x plus 3, got to multiply by a 1/2, plus 1/7 times the ln of x minus 2 plus a constant. And that, my friends, is the idea of partial fractions. And that's what we're going to need to use to find the general solution for a differential equation for logistic growth. So just to see how well you understand it, see if you're able to show that this integral is equal to this. So you can take a little time and practice that and see if you get the right answer. Maybe I made a mistake. Check it out. Okay, so here comes a long, fairly challenging problem. Everyone needs to do this at least once. So here we go. Here's a differential equation expressing logistic growth. Let's assume that we know what k is, and let's assume that when time is 0, the population is 20. And let's go about solving this. So if we separate variables, we get 1 over p times c minus p dp is equal to 0.008 dt. Alrighty, and what we do then is we integrate each side. And it's pretty easy to see that the integral of this is 0.008 t. We'll put a constant there. So the whole challenge is, how do I integrate this? And I'm going to use partial fractions to deal with that. So here's what we do. We start with, let's change our color. We start with 1 over p times c minus p. And what we say is, okay, that could have come from a over p plus b over c minus p. And if we go through our regular process of adding these two fractions together, what we'll get is that a is equal to 1/100th and b is equal to 1/100th. Yeah, I left something out, didn't I? I should have told you that c is equal to 100. So we're assuming that the carrying capacity here is 100. I knew that didn't sound right. So c is 100, c is 100, and that's why this comes out to be 100. So given that a and b are 100th, we'll factor that out, and we're looking at the integral of 1 over p plus the integral of 1 over 100 minus p. Well, the integral of 1 over p is just the ln of p. The integral of 1 over 100 minus p is the ln of 100 minus p, and we need this minus sign here because when I take the derivative of 100 minus p, I get minus 1. Okay, so if we pick that up, here's where we are. This is what we got when we integrated the left side. We already saw what we got when we integrated the right side. So we're going to do two things here. We'll multiply both sides by 100, and then we'll simplify this ln. So what that tells us is the ln of p over 100 minus p is equal to 0.8t plus 100 times c. And 100 times c is just another constant. We'll just keep writing c. Not a big deal there. And so what this means is that e to the 0.8t plus c is equal to p over 100 minus p. And we've already seen that we can take an expression like this, break it up as e to the c times e to the 0.8t. E to the c is a constant, so I can write this simply as a constant times e to the 0.8t. Told you this was challenging. So, making our substitution here, or our condition that p of 0 is 20, remember that? We just make that substitution. We get this, and what that means then is that 1/4 is equal to, I'm sorry, skip that for a sec. No, I think I had it right. So we get 1/4 is equal to a. And therefore what we can write is p over 100 minus p is equal to 1/4 times e to the 0.8t. Okay, so we're going to skip along and keep working on this. And as I've told you a couple of times, it takes a little while to get to the right point. So we'll continue on the next slide. Alright, so here's where we are. And what we'll do at this point is cross multiply. And so we'll get 4p is equal to 100 minus p times e to the 0.8t. 4p is equal to 100 times e to the 0.8t minus e to the 0.8t times p. So now I'll bring this over to the other side, and I get 4p plus e to the 0.8tp is equal to 100 times e to the 0.8t. And so finally we just move along, factor out the p, divide by the constant, and we finally get the expression that we have been waiting for. And here is the solution to that IVP, to that differential equation with some initial conditions. And notice this is a lot more challenging looking than the simple exponential growth. But you should check it out. You should check out when t is 0, we get 20. And when t goes to infinity, you should be able to check out that this goes to 100. Alright, so now let's look at an example. So I suppose we don't need to do an example because we really just did one. But I do want to mention in passing that were you to try to solve one of these equations, these differential equations, on either the Inspire or a TI-89, this is what you write. So it's a differential equation. Here's the differential equation. P prime equals that. We're given the initial condition. And what's always a little tricky about this is the independent variable followed by the dependent variable. And the fact that t shows up without having shown up anywhere here is something that takes a little while to understand. But remember, this is an equation for p in terms of t. So t is our independent variable. So you should try practicing with one of your calculators to make sure that you get the same solution that we got before. All right, so that's logistic growth. And that concludes Chapter 7, believe it or not. See you when we get to Chapter 8.